Welcome to The Explainer. We are diving straight in today because we're looking at an absolutely incredible journey. We're tracking a prodigy who managed to bridge two completely different worlds, the super practical, hands-on realm of engineering and the highly abstract universe of theoretical physics. By unpacking the story and insights of Sabrina Pasterski, we're going to see exactly how a mind hardwired for mechanics takes on the fundamental laws of nature.
14. That's the age our subject today flew an airplane completely solo. And get this, she didn't just fly it, she literally built it, herself. Before she was even legally allowed to drive a car, she had engineered an aircraft and taken it up into the sky. It's just a staggering achievement, and it tells you everything you need to know about her incredible drive. But, how exactly does someone even get to that point?
Section 1. The engineering mindset and building a real airplane. Her journey to that cockpit actually started in the Chicago public schools, where a simple third-grade science project on the magnetosphere sparked an absolute, lifelong obsession with space.
She and her parents took some incredibly pragmatic, highly structured steps to actually make this happen. Step 1. She started taking flight lessons at just 9 years old. Step 2. She hit the pavement networking at major air shows in Oshkosh, literally handing out Krispy Kreme donuts to aviation experts and government administrators to build connections, which, honestly, baked goods are a pretty top-tier networking strategy no matter what industry you're in. Step 3. She took over half her parents' garage to build a Zenith Zodiac aluminum kit plane. We're talking pneumatic rivet guns and thick instruction manuals alongside her dad. And finally, Step 4. Because you actually have to be 16 to fly solo in the US, she found a loophole and went up to Canada to do her solo flight at 14. She put in the hours, followed the instructions, and literally manufactured her own success.
Part 2. Pivoting to theoretical physics. Now, you'd probably think her path to Mars was totally locked in at this point. But as she grew older, that hyper-practical dream started to dramatically shift.
The really crucial thing here is understanding why she pivoted. First, there was a pretty harsh reality check. Despite literally building and flying her own airplane, she was rejected from Harvard and initially waitlisted at MIT. Around that same time, she started looking a bit more critically at the private aerospace industry. She worried that working in that field might just end up being about building glorified joyrides for billionaires, just nosing a plane up and down for a quick thrill, rather than genuinely pushing the boundaries of human knowledge. Plus, she noticed a huge trend. Her ultimate heroes, from the Nobel laureate who founded her high school, all the way to tech billionaires like Jeff Bezos, they all heavily idealized physics. She realized that if the people she admired most thought physics was the ultimate pursuit, she probably needed to follow suit.
So let's contrast these two worlds because the difference is absolutely stark. On one side, you have engineering. Building that kit plane in the garage was super straightforward. You've got parts, you've got clear instructions, you drill holes, pop some rivets, and boom, you have a physical machine that solves a problem. But theoretical physics? Entirely different ballgame. It is all about building abstract mathematical frameworks to understand the fundamental laws of nature. It's asking massive questions, like what actually happens when you fall into a black hole? And those questions definitely do not come with an instruction manual. In physics, the universe itself is the machine, and they're basically trying to write the manual from scratch.
Section 3. The hype and imposter syndrome. So she makes it to Harvard for grad school, but the transition wasn't completely smooth. It actually led to some pretty unexpected psychological hurdles. During her grad studies, her research on black holes, specifically this concept called soft hair, was cited by literally none other than Stephen Hawking. Suddenly, she is completely thrust into the spotlight. Forbes 30 Under 30 featured her. The media totally latched onto the story of the quote-unquote airplane-building girl who Stephen Hawking cites. But instead of feeling triumphant, this actually triggered massive imposter syndrome, which is something I think a lot of us can relate to when we're trying to prove ourselves in a brand new space. She was a junior grad student being hyped up as the next Einstein in the mainstream media, and to her, that title felt completely unearned within the actual scientific community.
Which brings us to the really jarring reality of the theoretical physics community. Unlike engineering, where a plane either successfully flies or it crashes, theoretical physics operates on a totally different wavelength. It's this tiny, highly insular community. We're talking roughly the size of a single auditorium. And because you can't just easily run an experiment to prove a theory of quantum gravity, success in this field is largely driven by opinion and taste. The crazy part is, the mainstream hype that her old engineering mentors thought was so amazing actually threatened to alienate her from her new peers, who tend to view flashy press with a lot of suspicion. She had to quickly learn that surviving in this field means navigating a super delicate sociology, relying heavily on mentorship and true peer acceptance.
Caught up in all the pressure of this hype, she initially panicked. She thought she literally had to memorize every single math textbook out there just to avoid failing. But she quickly realized that was a massive mistake. As she brilliantly puts it, don't read, compute. She figured out that theoretical physics isn't just about reading existing math. It's about building your own intuition by living inside the mathematics, really experiencing our 3D space plus time, and actively calculating things yourself, rather than just passively absorbing information. You have to compute to build the intuition you need to actually push the boundaries.
Section 4. Physics is just compression. She eventually took a faculty position at the Perimeter Institute, and this is where she truly began to synthesize her engineering mindset with theoretical physics.
This brings us to her core philosophy, which honestly completely demystifies the entire field. She views theoretical physics as an exercise in compression. Think about it exactly like compressing a massive computer file into a tiny zip folder. Physicists are basically trying to find simple, elegant, underlying mathematical descriptions that can explain a massively complex variety of natural phenomena. It's all about boiling the universe down to its most fundamental, efficient code. It is just an absolutely brilliant, breakthrough way to think about how the universe operates.
And you can see this compression at work everywhere across the field. Just look at the Standard Model. With just a handful of elegant, simple assumptions, physicists have mapped out this vast, comprehensive understanding of particle physics. Or look at symmetries. When you know that energy is conserved within an isolated system, you instantly need way less information to understand exactly how that system behaves. And then there's quantum gravity, which is basically the holy grail of modern physics. It's the ultimate compression project. It seeks to take the large-scale physics of general relativity, combine it with the microscopic physics of quantum mechanics, and unify the whole shebang into one single, simpler framework.
So how exactly does an engineer tackle this ultimate compression project? Well, she had a massive breakthrough. She realized that she could treat the dense, deeply overwhelming mathematical corpus of theoretical physics itself as an engineering challenge. Instead of just doing math on a chalkboard all day long, she noticed that complex dualities in string theory were very often just redundancies. It was basically different papers saying very similar things in slightly different ways. So she asked the golden question, why not treat that as an engineering problem?
She decided it was time to modernize the approach. Why rely solely on pen and paper when we have modern tech? She's now excitedly championing the use of data science, computer science students, and semantic search to automate and fully map out the theoretical physics literature. By treating decades of literature as a massive dataset, interdisciplinary teams can find links, strip out the redundancies, and drastically accelerate new discoveries. The kid who built airplanes in her garage is now essentially project managing the universe, bringing hardcore resource allocation directly into the purest of theoretical sciences.
Which leaves us with this final, incredibly provocative thought. For decades, major institutions have just hoped that fundamental physics would eventually trickle down into practical, real-world technologies, things like quantum computing or better GPS. But what if the flow goes the other way, too? Shouldn't we be using today's cutting-edge technology in engineering teams to actually map out quantum gravity? It is just a brilliant full-circle moment. From a kid building an airplane in a garage to a physicist engineering the very study of the universe itself. And it really makes you wonder, what other massive abstract mysteries in our world are just sitting there waiting for an engineer's practical touch? Thanks so much for learning with me on this explainer today, and keep exploring.